From SETI to CERN, what you need to know about cluster computing and how it can help your enterprise. Remember SETI at Home? The Institute for the Search for Extraterrestrial Intelligence, SETI, once managed gigabytes of radio telescope data collected from observatories worldwide, a feat back in the early 2000s. When programmers hit upon a novel solution, they realized that instead of relying on one massive central computer to process all the data, they could let users download an app to their own devices. It was essentially a screensaver that kicked in after a few minutes of inactivity, downloading small chunks of data to analyze. The results were then sent back to its UC Berkeley base, offering a visual representation of the data synthesis process. At its peak, SETI at Home had around 2 million active users, a number that still makes it one of the most recognizable uses of cluster computing. Cluster computing involves a network of interconnected computers or nodes working together to perform complex tasks. These nodes often consist of low-cost, off-the-shelf hardware, and they collaborate to analyze large datasets. At its core, cluster computing is about distributing workloads across multiple machines to achieve faster and more efficient processing. This approach isn't just theoretical. It's been applied in real-world scenarios like scientific simulations, big data analysis, and financial modeling. Even without a supercomputer with unlimited processing power, cluster computing remains a vital tool for handling AI-driven workloads. What sets cluster computing apart is how its nodes are arranged and coordinated. Each node typically runs a simple task, and the middleware software manages how these tasks are divided and executed. For example, a single node might handle a specific part of a dataset, while another processes a different section. This distributed approach ensures that even if some nodes fail, the system continues running smoothly. In fact, fault tolerance is a key feature of cluster computing. If one node goes offline, the system can reroute tasks to other nodes, maintaining performance and reliability. Cluster computing isn't just about speed, it's also about cost-effectiveness. By leveraging existing hardware, organizations can build clusters that are far cheaper than investing in custom-built supercomputers. Plus, clusters are highly scalable. Adding more nodes simply requires more memory, storage, or processing power, which can be done without major disruptions. This flexibility makes cluster computing ideal for businesses with fluctuating data needs, whether they're using cloud computing or managing resources on-premises. But cluster computing isn't without its challenges. One of the biggest hurdles is managing the complexity of a multi-node environment. As nodes are added, the system becomes harder to monitor and maintain, requiring robust middleware that can handle diverse operating systems and communication protocols. Some applications may also struggle with parallel processing, necessitating reprogramming or updates to fully leverage cluster capabilities. Additionally, cluster computing relies heavily on network speed and availability, a factor that can vary depending on the size and scope of the network, such as the public internet. Here's where it gets controversial. While cluster computing is often seen as a cost-effective alternative to supercomputers, it's not always the best choice for every task. Supercomputers are designed for high-performance, specialized workloads with tight integration between hardware and software. They're built with purpose-built processors like Cray, AMD EPYC, or IBM Xeon chips optimized for low latency and high bandwidth. In contrast, cluster computing uses commodity hardware like consumer laptops or servers and relies on flexible middleware to coordinate tasks across a network. Is cluster computing the future of computing? It's a question that sparks debate. While it offers scalability and affordability, it also requires careful planning to avoid complications. For businesses looking to harness the power of AI, cloud computing, or big data analytics, cluster computing provides a powerful middle ground. But as technology evolves, will we see more hybrid models that combine the strengths of both cluster computing and supercomputing? That's a question worth exploring. In action, cluster computing powers everything from AI research to space exploration. The UK's AI Research Resource, AIRR, uses cluster computing to run deep learning models and simulate complex datasets. Google's compute engine leverages cluster computing for real-time search indexing and AI training. NASA's Pleiades cluster simulates space missions, while CERN's worldwide LHC computing grid processes petabytes of data from the Large Hadron Collider. These examples show how cluster computing is shaping the future of data science and technology. As the demand for faster, more efficient computing grows, cluster computing remains a critical component of the tech landscape. Whether you're a researcher, business leader, or student, understanding how cluster computing works can help you make smarter decisions about your digital infrastructure.